Good morning and welcome to Calix's post-AGM webinar on the 11th of November 2020. This morning we have CEO and Managing Director Phil Hodgson, who will provide a brief general update and then specifically focus on the company's highly prospective battery development program. As a reminder to participants on the line, if you did want to ask a question, you can do so via the Q&A box at the bottom of the screen. I'll now hand it over to you, Phil. Please go ahead.
Excellent. Thanks very much, Simon, and thanks all for joining me this morning. Post our AGM, which was held at 9 a.m. Daylight saving time. So I'll get into the presentation. As Simon said, what I'll do is I'll cover off a little bit about the recap of who we are, our business overview, and then how we're going so far year to date. But of course, spend most of the time today on a bit of a deep dive, if you like, into our battery development program and how that's progressing. So without further ado, let me just, for those less familiar with the company, perhaps give a brief overview of what it is we do. Well, first of all, I'll give a snapshot of I guess, the business globally. We do have parts of our business in the States, parts in Europe and parts in Australia. We are growing our sales revenues, certainly from an Australian base into Southeast Asia and also now into the States, mainly based around our water business and water treatment business. We do have quite good control of our supply chain, so we've got our own mine here in South Australia, and I'll go into what we're mining there and how that then plays through into our revenue producing businesses in wastewater treatment. And we're also pretty quickly scalable, so we have a full-scale commercial facility at Bacchus Marsh in Victoria, which is about only 15% utilised currently. So without huge amounts of further capital, we can actually scale the business quite quickly. We've got a pretty robust business model. Our commercial contracts are with municipals, industrials, and for wastewater treatment. So despite things like COVID, we've continued to grow our revenues quite successfully over the course of the last 18 months. We also have quite a good funded development pipeline, so we've been very successful getting funding for our businesses. And we've got some great multinational partners we're working with. So our European business is mainly focused and concentrated around the CO2 mitigation application of our technology. And there we're working with some quite large multinational partners such as Heidelberg Cement, Lewiston Cemex, cement and lime companies, but also companies like Solvay, who are a chemical company, Engie, a utility company. And when I talk a little bit about that part of the business, I'll sort of make more sense as to why the companies like that are working with us. So quite a good sort of snapshot, if you like, of where we are. We're a cash positive business, we've got no debt, and we're growing our revenues very successfully. So just in terms of what is it that we do, we're actually a technology platform company. All the different verticals that we're in are all based upon that one core technology, and it's a reinvention of the kiln or furnace. But instead of doing it the same way as everyone else has done for 5,000 years, we do it a little bit differently. We start with a central reactor tube, and I've got a little toilet roll here to illustrate our reactor tube. But in Bacchus Marsh, this is 22 metres high. It's about 1.8 metres in diameter, and we heat it up to 1,000 degrees centigrade. And whatever it is that we want to try and heat up, instead of having all of the furnace flames or heating medium contacting the particles, we heat it through this tube. So we have the heat on the outside, and then down the center of the tube, we put the material is that we want to heat up. We grind the material up to sort of a fine powder. And basically just imagine you've got a lump of flour in your hand and you just drop that flour and it sort of floats down. Well, that's what's happening inside the tube. We've got our material that we want to heat up, ground up, and it floats down through the tube. And as it does so, the sort of 1,000 degree walls are glowing red hot. So they're transferring the heat into the powder. Big deal. What does that mean? Two big advantages come from doing it this way. The first advantage that we have is CO2 capture. Now, how does that work? Well, if we start with limestone, half the weight of a lump of limestone is CO2. And currently, all the cement and lime companies are heating up that limestone. When all that CO2 is coming out of the limestone to form lime, and that's mixing with their furnace gases and heading out their stack. And so that's what's making the cement and lime industries the most CO2 intensive industrial process. They're responsible for 8% of CO2 emissions. Now with our process, you can imagine heating from the outside, with the limestone and cement mill going down through the centre of the tube. As the CO2 comes out of the limestone, it makes its way back up the tube and out the top again. And so that CO2 comes out the top as a pure stream. And so 2/3 of the emissions of the cement and lime industry are coming from the limestone itself. And we have a technology that can capture that directly. And that's the technology we're developing in Europe with the Heidelberg Cements of the world. The other key aspect of the technology is as we pass these particles through, and just say we start with a different mineral, and we start with a mineral called magnesite. And this is the mine we have in South Australia. We're mining this material called magnesite, and we pass it down, grind it up and pass it down through the tube. We can actually maximize what's called the porosity or surface area of those particles. So as those particles fall, the gas inside the particles come out, and we can maximize the porosity of all the gases coming out and leaving a honeycomb type structure. And that porosity or surface area, that equates to reactivity. And so when you've got more reactivity, that gives you competitive advantage in quite a few different verticals. And so we can start with magnesia, and we can make products for wastewater and aquaculture, lake remediation, in fact, crop protection, all based upon this same raw ore magnesia. We can also start with manganese. And manganese is one of the things that we're using and looking at to start to produce battery materials from. And again, maximizing the surface porosity and reactivity of manganese-based materials is the core of our battery treatment technologies. So so that's the core, if you like, of the technology. Patent protected. As we develop new applications, we not only have the core technology patented, we also have each of those applications protected as well. And a lot of capital's gone into developing this technology. Just looking back quickly over our results last financial year, and then I'll quickly cover off what we're looking at this financial year. So last financial year was a very transformative year for the company. We completed an acquisition in the US where we're taking our technology and we're putting it into an existing business in the US to really leverage growth there. That business that we purchased in the US really helped our sales revenues as well. So from financial year prior to last financial year, we had a massive growth in sales revenues as a result of the successful acquisition coming and laying across our consolidated financials. So you can see our sales revenues jumped 327% as a result of that acquisition, but also our raw sales revenues in Australia and New Zealand and in Southeast Asia, that grew 34%. So we're going quite well here in Australia, but we've now got a much larger base to grow off into a very big market in the US as well. And overall revenues grew 76% to over 24.4 million. So those additional revenues on top of sales, revenues that we're getting for projects and grants. So we're very successful getting project funding and grant funding to help develop our technology as well. So last year, a big jump in overall revenues, a big jump in sales revenues as a result of the acquisition in the US. I'll talk a little bit about that in a sec. So overall, a very successful and transformative year for us last financial year. If we're looking to this financial year, our priorities for financial year 21, across each of these verticals that I described before, in the water and wastewater space, we're already in market. And that US acquisition was the major step up that we took last year in that market. And there's several things that we're trying to achieve in that business this year. I'll talk about that vertical a little more. And I did cover this at a webinar on last Friday with NWR, and that webinar is available for those who wish to register and go into that in more detail. But I will touch on that in this talk as well. In aquaculture and freshwater lake remediation and agriculture, we're in that pre-commercial phase. Both of those are starting to move through and earn some revenues. And then also in the CO2 mitigation space. I'll talk a little bit about that today, but again, more detail in that webinar from last Friday. And of course, today, I'm going to do a deep dive on the advanced batteries vertical in our business. Just in terms of wastewater treatment, so I'll touch on this in the CO2 part of our business. You can see there so far this year, we've continued to grow our revenues compared to prior periods. So just in this period up to end October, we're targeting 3 more US plant upgrades. So that's taking the existing business that we purchased there, putting our technology into it, and then generating more revenue and margin as a result. So if we can make a more stable product based upon magnesia that goes in that wastewater treatment business, we get logistics advantages, we get some cost of production advantages, and that moves through into gross margin growth and revenue growth. So taking our technology into this platform in the US is one of the key things that we're trying to achieve well this year. We've already achieved one plant upgrade, so we've got 2 more to do, and we've got 1 new plant to build this year as well. And so that US piece is really a big focus of what we're trying to achieve this year. And already you can see that we're starting to get some good results lay across the first 4 months of the financial year. And specifically, I'll draw your attention to gross margin, because you're starting to see there where our technology is leveraging better margin out of the business that we purchased in the US. And really, the strategic reasons why we purchased that business in the US are starting to play out well for us. The other thing that we'll cover off very brief that we're trying to achieve this year is taking what we did in the US and trying to replicate that in Europe. And so we've done some very successful trials in Europe over the course of the prior financial year, and we've to date this financial year achieved our first paid trial in Germany. So overall, the wastewater treatment business, again, just touching on it very briefly today, the wastewater treatment business is off and running really well for us this financial year. So ticking off those milestones, and as I say, probably even a little bit ahead of where we thought we might be on gross margin. Just in terms of CO2 mitigation, again, just a slight deep dive into this, more detail in that webinar that's available. With the CO2 part of our business, we have an existing pilot facility that was built in Belgium. That pilot facility is taking 5% of a slipstream of a major cement plant, demonstrating that CO2 separation that I talked about before, and then re-injecting that back into the cement plant. So when we turned it on, we proved the technology concept, and we've been running it since about mid last year to continue to prove up that technology in terms of its operational robustness and gradually increase throughputs and temperatures to take it up to full nameplate capacity. Suffice to say, one of the things that we achieved last financial year was that technology was already prospective enough for the EU to give us a further 16 million euro to scale up to what we're calling our LEILAC 2 project. LEILAC is low emissions intensity lime and cement. And so that scale up is now funded as of December last year. We signed the project agreements for that in April this year. And those project agreements involve cash and in-kind funding from our industrial partners involved in that scale up. And so the real momentum is starting to build behind this CO2 mitigation part of our business. And why is that? Well, I think people may not be aware, but in 2018, the EU ratified a reduction in the cap on the emissions trading scheme. That action saw the price of CO2 in that cap and trade system jump from 5 to 25 euro per tonne. So there's an economic driver for companies to mitigate their CO2 in Europe. Not only that, one of our major partners, Heidelberg Cement, they've targeted net zero CO2 by 2050 and a 30% reduction by 2030. So these companies are now taking their own initiatives to reduce the CO2 emissions, and technology is the only way they're going to be able to do that. And then in 2020, just this year, the EU legislated net zero CO2 by 2050. So there's a real momentum starting to build behind CO2 mitigation. Europe is leading the charge, but who knows if the US election result is ratified, the US has already indicated that it will also be targeting net zero CO2 by 2050. And so there's a real, I guess, tailwind that's starting to blow much, much harder around CO2 mitigation. And cement and lime, as I said, the highest industrial emitters of CO2 at 8% of global CO2 emissions. And these guys have to do something about those emissions. So despite the fact that we've still got a couple of years, certainly to play out with LEILAC 1, the runs there should finish about mid next year. We've got the design phase of our LEILAC 2, and LEILAC 2 will be up and running by late 2023. Despite the fact that that as being our sort of first commercial scale demonstrator will only be available then and tested then, we're getting a lot of interest even right now in looking at LILAC-3 type concepts, and LILAC-3s are, if you like, the full-scale versions of the technology. And so we're in discussion with quite a few parties, and we've tried to give an idea or snapshot of the parties that were in discussion there around different aspects of that CO2 mitigation: refractories, cement, and lime. And so targeting this year, it'd be great to move through to at least 1 to 2 licenses, covering the first full-scale plant and a feasibility study underway. So certainly a lot happening in the space around CO2 mitigation. And you know, one of the reasons we highlighted is that this part of our business is accelerating quite quickly. Okay, right. For those who've been tuning in just for the battery materials development part of the program, apologies. Hopefully the first bit wasn't so boring for you. But now I'm going to touch on this particular vertical. This particular vertical in our technology, we really only launched about a year ago now. And so while we always thought that we had a unique technology to start to look at these sorts of things, if you remember that sort of honeycomb type particles that I described before, why would they necessarily be great for a battery material? Well, with a battery material, you know, the lithium ions have got to get in and out of the anode and the cathode of the material. And so there could be some great reasons why high surface area porosity would improve the performance of a battery, you know, energy and power. And so what I want to do today is cover off our advanced materials battery program, but sort of give it the context, if you like, for those who are less familiar with battery technology. And I'll start a little bit, well, certainly here's our vision: cheaper, safer, better, and more environmentally friendly battery materials. So there's our moonshot, if you like. We want to do it all. And we're only 1 year into it, but everything's pointing very positively to try and hit this sort of moonshot. Why batteries? I think this should be fairly obvious to most people. The forward projections for lithium-ion batteries are phenomenal growth. We've looked at many different sources, and I'm sure you guys have as well, but electric vehicles, mainly the driver, along with significant growing contributions from things like stationary storage, like the big battery in South Australia, for example. All of those are driving substantial growth over the next decade. And so while there's numerous theories as to how fast it'll grow and what it'll get to by when and all those sorts of things, I think what we can say from this graph and from numerous others that we've seen, growth will be driven by electric vehicles with some significant contributions from baseload storage, and it's going to be very fast over the next decade. So it's a very interesting industry to be in as at, you know, 2020, right at the start of this particular curve here. So lots of potential, lots of potential. Potential is an interesting word to describe batteries because, anyway, if I have a look at how do lithium-ion batteries work, I want to sort of spend a little bit of time here just so people, when I talk about a cathode or an anode, people understand what it is I'm talking about. So I've got a little diagram here on the left-hand side of the screen, and this is sort of a schematic, if you like, of a typical lithium-ion battery. You have this conducting medium or terminal substrate, and for the cathode, it's typically aluminium. And the actual cathode itself is a collection of crushed crystals in sort of a glue, if you like, and that's sort of glued to the aluminium. And in between, and touching the cathode is this thing called the electrolyte. And the electrolyte's job is to transfer lithium ions from the cathode to the anode. But you don't want the cathode touching the anode, so you need a separator. And this separator allows lithium ions to go through, but doesn't allow any materials from the cathode to touch the anode, because of course that will just short the battery. And then on the other side, here you have the anode. And so when you're charging a lithium ion battery, you've got all your lithium ions moving from the cathode here down to the anode. And when you're discharging the battery, it's moving the other way. And so in the anode itself, the terminal substrates are typically things like copper. And so in discharging a battery, you're obviously producing power out of those terminals. And when you're charging the battery, you're trying to put power into this anode material to force the lithium ions back up in the cathode here. So that's the sort of, I guess, way a lithium ion battery, and indeed most batteries work. But I wanted to describe that because the cathode is the source of lithium ions in a battery. So it sits there, you impregnate the cathode with lithium ions when you make that cathode material. And then, of course, the first discharge, those lithium ions move across the anode. So the cathode, as the source of lithium ions, it's the main determiner of capacity and voltage in the battery. So the cathode is a pretty important material in the battery. All of these things are important, of course, but cathode's pretty important. And the other thing that makes cathodes pretty important is the cost. Cathodes, in terms of the average cost structure of a lithium-ion cell, are well over a quarter of the cost of the cell. And so many, when you look at the take-up, for example, of electric vehicles, many pundits are saying you've got to get the cost down to get electric vehicles more widely used. Well, sort of a bit of push and pull. I think, you know, the more wider the use of electric vehicles, the cost will come down. But one of the key areas that you can take cost out of the battery is of course, the largest segments, and the largest segment of cost is cathode. So if you can find a way to reduce the cathode cost, be it materials, be it energy, or be it the capital. What I mean by that is you know, the complexity of the plant that's used to make the cathode, for example. Then obviously that's sort of the low-hanging fruit, if you like, on getting the cost structure down of a lithium-ion cell. So that's a little bit on how lithium-ion batteries work. The next little graph, I want to talk a little bit about the key operating properties of lithium-ion batteries. And the typical properties that are described are what's called the Ragone curve. On one axis, if you like, you have energy, and on the other axis, you have power. Energy, if you like, is the size of the fuel tank. Power is how fast you can get the energy out of that fuel tank, how much fuel you can get out of the tank. So typically batteries fall along those two curves. And along the power side, the bottom, are typically what's called capacitors. So these are things that really deliver a hell of a lot of power really quickly, but then that's it. They don't really have a whole lot of fuel in the tank. They're there for punch. On the energy side, you have batteries in that sort of side of the curve that really have a lot of energy. They can deliver energy over a long period of time, but they can't really give a whole lot of power. And so typically electric vehicle batteries are up in this energy piece because people are really interested in long range, obviously for the batteries and these sorts of things. But increasingly, they're trying to move into the power bit, because power, not only in delivering the punch, but also accepting a punch. How quick could you charge a battery? Typically, the power curve starts to determine those types of properties. And so what you've got here is a situation where if you're making supercapacitors, you'd love perhaps for those supercapacitors to have a bit extra energy. And if you're making typical batteries, lithium-ion batteries, you'd love for those batteries to be able to have a bit more power and charge a bit faster. And so I've got both of these things heading up towards what I'm terming battery heaven. You know, how do you push this Ragone curve out? High power, high energy, and of course, you know, low cost and safe. And what I mean by that is it's great to have high energy and high power, but if your car is going to cost you $1 million to get the best energy and the best power battery you can find, you're not going to sell many of them. The idea here is to try and not only combine energy and power, but cost and safety. And this next little table here, bear with me as I take you through it, this starts to look at the different cathode chemistries along those different parameters. So yeah, here are the top 4 chemistries, and forgive the nomenclature, but NMC or NCM, that's nickel, manganese, and cobalt in the battery. So they're the key elements in the battery. Manganese is by far the cheapest element in that one. Nickel is getting much more expensive, and cobalt is very expensive. NCA, nickel, cobalt again, and aluminium. And LFP is iron and phosphate, and LMO is just plain old manganese. And if you have a look at the stability, voltage, energy, cost, and safety, all of these things play into how successful these battery chemistries are going to be in a car. The very first modern electric cars, like the Nissan Leaf, were using the lithium manganese oxide, these ones here. And they had reasonable energy. Their cost was way down. So that's where they had a key advantage. They had good voltage or good potential. Stability wasn't that great, so the batteries would deteriorate over time, but the safety was good. Generally, they were fairly safe. Increasingly, the Teslas of the world, etc., have gone for mileage. They want more energy. And so they've gone to these sorts of chemistries like NMC or NCA, and they've gone for mileage. Now, that brings with it some problems. Cost is much higher. Safety is an issue. And stability, while probably better than certainly for NMC versus lithium, hasn't been tops, but it hasn't been too bad either. Increasingly, originally there was a lot of lithium iron phosphate around. And what's interesting here is, not the best in terms of energy density, but really quite stable, good safety, and not too bad on cost either. And interestingly enough, LFP have become the battery of choice for Tesla for their Model 3 for China. So they're going for not necessarily the furthest mileage you can possibly imagine, but they're going for a long-term battery that will be stable and reasonably cost-effective. So all of these things are at play when you're looking at the electric vehicle market, and indeed even the stationary energy storage market. All of these things are at play, all of these factors, not just energy, but cost, safety, stability. Okay. One of the things that was very interesting at the recent Battery Day was Tesla announcing that they were moving to manganese. Manganese in combination with nickel being a key strategic development pathway for them. If remember on the last slide, I talked about the Nissan Leaf and the focus on lithium manganese oxide, or just the manganese chemistry. This is sort of an interesting shift because while EVs were moving away from manganese initially over the last few years, this announcement by Tesla is indicating a shift back to manganese. Remember, manganese is the cheapest by far element in a lithium ion battery. They're looking at combinations with nickel to keep that sort of mileage and stability up. But interestingly, in China, on the graph on the right here, you can see that LMO, or the manganese, is in fact the fastest growing part of the market in China. And what's interesting there is they're using the LMO, the manganese-based chemistry, to blend into other chemistries. So they're sort of using a combination of the other chemistries and the manganese to keep the costs down, but to keep the performance and stability up. And so manganese, which was sort of shrinking away a little bit as a poor cousin, is actually sort of firmly back on the table as a potential chemistry in this growing market. So, enough of the battery technical talk and market talk. Why Calix? Why our materials? What I've tried to do here is illustrate the difference, if you like, between the current cost, the current manufacturing, and most R&D development is happening down sort of this route along the left-hand side. And what that is exotic chemistries, interesting ways to then take the particles that are produced out of those chemistries and sort of glue them together, layer them, or do whatever, and they sort of assemble these crystals. And the more exotic the methods, they're starting to get sort of slightly better performance, but of course, the more exotic, the harder it is and the more dollars it is to scale. So what do we do? If you can remember our sort of toilet roll, what you can see there is a picture of a sort of mini toilet roll, if you like. That's our what's called Batman reactor, 18 meters high, little 8-inch tube, electrically heated. We just take manganese carbonate, agricultural grade. It doesn't have to be battery grade. I'll talk a little bit about purity in a sec, but we just take agricultural grade manganese carbonate. We grind it to small particles. It gets dropped down that tube. And the manganese carbonate has that trapped CO2 in it, as I described before. That makes its way out, and you then have a very porous material that comes out the bottom. We can control that porosity to give a nano structure, if you like, to these crystals that are microns in size. And so you can see the difference here between an assembled structure and the way we make our structure. And so we're already at commercial scale. This tiny little Batman reactor we produced here is already a 2,000 tonne per annum sort of rated capacity. It cost us less than $2 million. And so if you think about, first of all, material cost, and you think about capital, which are two key things that, were part of the cost of a cathode material, we're already starting with very low cost materials. And we've got a process that's very low capital intensity. And so how do these sorts of chemistries start to compare in terms of the way they perform as a battery? I'll talk about that shortly. The second little piece I want to talk about is, well, it's great to produce your raw crystal, but remember, I said before, you've got to get your lithium into it. And traditionally, what the current methods use are taking what's called a lithium carbonate, which is a solid. You mix that with your crystals and you shove it in a furnace for 12 hours. And could be much longer than 12 hours, in 12 minimum. And this route here, why we're interested in the nanoporosity, apart from the strength of the crystals we're making and that controlled porosity, is we can use a liquid sort of doping solution here. So we start with a lithium hydroxide, and we're trying to get the sintering stage down as much as we can. And so where are we at with that process? Well, here on the right-hand side, we've got an interesting graph that looks at, well, here's your standard 12-hour sintering, this very top curve here, and here's the performance in terms of, say, specific capacity versus discharge rate, or that power side. And so here's a typical 12-hour sintering route, and here's what happens when you drop that sintering time with this solid methodology. So you drop that sintering time to, say, 2 hours, and you can see the dramatic performance reduction that occurs in the battery. Well, here's where we've used our liquid lithium hydroxide solution doping technique, and only sintered for 1 hour. And you can see here, we're not quite up at the 12 hours yet, but we're getting close. And so this is a really interesting way. Remember, I talked about material, I talked about capital, and I talked about energy being the three things that are the key inputs in the cost of a cathode material. This is really a demonstration that we can move quite some way to reducing the energy that's required to produce a cathode material. Early days, got to emphasize that, and more testing is required. But this particular type of lithium lithiation, it's called, or lithium doping, is high potential to reduce that energy component in making a battery material. So they're the three sort of areas that I think our technology is very suited to making battery materials, and why we started on this journey. Low capital cost and simple route, starting with raw materials that are very simple, and lowering the energy. What I'll talk a little bit about here is the raw material now. If you remember, I mentioned agricultural grade manganese carbonate is what we're starting with. We're not starting with high purity materials. And this table here, I know it's a little complex, but here I'm trying to describe the different impurities in materials. And here in these two columns, you can see the standards that are, these are Chinese standards actually in place now for lithium manganese oxide materials. And you can see some of these things called impurities here, and these are just elements like potassium and sodium and calcium and iron, and they've got to be very low. So in typical battery material processes, you've got to start with low impurities. We tested some commercial grade LMO, and when I go through the test results further down, you can see here that in most cases they're conforming to these types of standards. Well, here's us. We've got pretty dirty LMO. Well, let's be honest. We've got high calcium, high iron, high copper, and high magnesium compared to the standards. Well, actually very high compared to the standards. So can we take sort of fairly dirty materials and make some decent battery out of it, materials out of it? And so, you know, when you're starting with sort of this level of impurities in a standard process, a lot of battery chemists would be throwing their arms up in the air. Why would you be doing that? Let's just see how we performed in the next few slides. Okay, despite lower purity, encouraging performance. Now, this LMO benchmark, you can see the error bars on it. So we've tested this many times. And so we're looking this laid up against lithium manganese oxide cathode material in a half cell test. That's a commercial grade material. You can see the classic decline in performance that is typical of manganese oxide batteries. They're not very stable as you start to increase the discharge rate. And you can see our material here is very different. So over on the right, you can start to see, we've taken some photos, magnification, obviously, quite high magnification of those different materials. You can see here, this is the commercial grade material. It looks like sort of those hard crystals, you know, fractured up a little bit. And here you can see, I guess, some remnants or evidence of that sort of high porosity morphology that goes into our crystal manufacture process. Very different process. And so as an indicator, if you like, of the differences in performance, this could be a first step to sort of say, well, clearly there's a different morphology or different structure of the crystal. And that is certainly a part of what we thought that we would see when we started this journey. And these results, again, after numerous tests with those error bars, have borne that out. We can take it up to very high discharge rates without a substantial loss in our capacity. So at 20, what's called C discharge rate, we're discharging this material in 3 minutes. So it's a very, very fast discharge rate. And typically, most manganese structures do not handle that. That's why this commercial material hasn't even been tested beyond. So first of all, less pure, all those sorts of things, but performing very well. So we thought, okay, well, let's not just do one, try and test it against one thing. And that we tested both the commercial LMO and our own in the same way. But we thought, well, let's have a look at the literature. What does the literature say? And we've looked at all of the commercial LMOs we could find literature on and plotted them. And we've looked at all of these really exotic materials that have been made in a lab. I really love nanothorn and hierarchical porous onion and resorcinol formaldehyde root. So they all sound very highly scientific, but also, I'd imagine, extremely expensive and hard to scale up routes to make exotic type materials. Ours, we've never just got the particles and threw them down a heated tube. Well, obviously a bit more than that, but that's basically the technique we use to get to the raw manganese oxide. And so you can see here, again, same plots as on the previous graph, but added these extra plots from the literature where we've compared it as best we can. We're certainly ahead of any of the commercial LMOs on the market in terms of the published results. And these green lines here, which are all the lab LMOs and with some really exotic techniques to make them, we're sort of starting to push up into that green area. Again, we're only 1 year into our program. We're hoping we can keep moving this line higher. But clearly, we're starting to move into a very interesting and prospective part of the performance curve for these materials. And how do we compared a whole lot of standard lithium manganese oxides, some exotic lithium manganese oxides, but LMO or lithium manganese, what else? How do we compare against other chemistries? Now, remember I talked about lithium iron phosphate and the fact that Tesla is now moved to make all its Chinese-based Model 3s with lithium iron phosphate formulations. We've decided to plot that in terms of things like energy and power. Remember that original plot I had at the start of the talk, energy versus specific power? Well, here's where lithium iron phosphate sits. You know, it's actually not too bad once you, in terms of energy density, but starts to fall away when you talk about its power output. And so we're sitting here. Here's our curve against this lab-made but commercial formulation lithium iron phosphate. And of course, here's the commercial benchmark that we've been testing as well. And so against other chemistries, certainly not, we haven't put ourselves up against the much more expensive chemistries yet, but against lithium iron phosphate, which is a highly commercial and high growth chemistry. Our chemistry is looking looks like it's got very good potential. And so really a question that comes to mind from this one is could we actually compete with this material in the lithium iron phosphate market as well? So in terms of the results to date, early days, we've got a lot of work underway. You can see here a very busy slide, but that covers, this is the sort of network, if you like, of all the different initiatives and partners we're working with in our battery program. Most of the work that I've described the results for sit up here in our CRCP for advanced hybrid batteries. This is where we got the 3 million in funding from the Australian Government, Department of Industry, Innovation and Science to develop advanced hybrid batteries. And so with Boron Molecular, Deakin Uni, this is the area that we've been working on and a lot of the results I've been reporting against. We're also part of what's called the Future Battery Industry CRC. There's a whole nother piece of work that's happening in here. We're looking at spodumene processing for lithium beneficiation, again with the same core technology. There's some very interesting and large partners as part of this program. And so that particular piece is about setting up a battery industry here in Australia. Down here, we've got the Poly Storage Network we're working with. That's a European network looking at solid state batteries. So while I've just spoken about lithium manganese oxide, in the FBI CRC and in the Poly Storage Network and even in the Store Energy Network, which is over here, we're looking at many other chemistries, all of which could be enabled by our technology to be cheaper, lower capital, lower energy. So a large network, you can see the names there, some pretty big names. And so while we're only 1 year in, we're already getting some very interesting results, and we're working with some great partners that are helping us on this journey. So we've still got quite a bit of work to do. As I say, we're 1 year in. Where do we go from here? In terms of full cell performance, all of the results we've seen are what's called half cell. So just the cathode with a whole lot of lithium there. How has that worked? Well, we've got to combine that now in a full cell. So we need the anode material. We need to develop, along with our partners, Boron Molecular, the right electrolyte. And so we want to optimize that. And we need to then do lots of charge and discharge cycles. So how stable is the material for 500 or 1,000 or the sort of golden number that people are aiming for now with car batteries is 3,000 charge discharge cycles, 3,000 being the 1,000,000-mile battery that Tesla are after. And so really over the course of the next 12 months, that full cell charge discharge cycling performance will be a key performance indicator for us and a key milestone for us. We obviously want to then expand into field trials where we put battery packs together and look at a real world application, whether that be sort of a car pouch or an e-bike pouch or something like that. And so through 2022, that's the target there. We also want to scale up. So we've been dropping grams, well, probably kilos at a time, but certainly grams through our Batman reactor. We can scale that up to kilograms per hour and then ultimately tons per day. But that has to be part of an overall production process that then also includes that lithiation stage I mentioned before, and then ultimately the assembly process as well. So this scale up piece, we can get the first stage done pretty quickly because we've already got a reactor plenty big enough to do that, but then moving to those other stages of production, adding the lithiation process, etc., and the assembly process may take us out a couple more years after that. In terms of the stuff that we'll continue to do in an iterative and ongoing way, we'll continue to optimize the LMO. If you can remember, we've only got sort of one benchmark curve there. We've made lots and lots of different samples, and there's lots and lots of things we can do to try and shift that curve up still. We're only 1 year in, but we think we've already got some ideas about how to continue to shift that curve up and make that better. And the other thing, of course, is it's more than just LMO. If you remember the previous graph, we're working with a whole lot of different parties across a whole lot of different chemistries. And so starting to even introduce nickels, starting to look at anode materials for the same types of properties, strength, controlled porosity, lower energy, lower capital. They're all on the drawing board, and that will be an ongoing test program. And then the electrolyte optimization. As I mentioned before, we've got Boron Molecular we're working with in the CRC-P, and what combinations of anodes and cathodes and electrolytes really work best in an overall cell. That's going to be iterative and ongoing as well. So quite a development program that's still going to take at least another year or so for some really interesting early work to be done on the charge-discharge cycling. And also as we then move to look at how we scale up, optimize, etc. So, but we're not talking decades. We're talking in the space of a year to get some really interesting results to understand whether we've got something really special here. So just summing up, LMO is the start. The manganese oxides we've started, but even LMO has great potential that we see. We still see the potential for far lower costs, as I said before, capital, energy, materials. We've got some very strong early performance results up against certainly the commercial benchmark LMOs. We're outperforming, and even LFPs. And the very sort of exotic lab-derived LMOs, we're starting to get up into the mix of those. And remember, we've started with a ag-grade manganese carbonate as our source material. So we've got some very strong early performance results. And highly prospective markets, as I say, LMO is just the start, but I think LMO has great potential, but there's lots of other chemistries to be tested also. So there's the team standing outside the Batman reactor at Bacchus Marsh on the right. Of course, the teams from Deakin Uni and Boron Molecular are also very important members. They were too embarrassed to send their photos in, I think, but I'll include those guys next time. And of course, the wider diaspora of all the companies and institutions we're working with will continue to add to the team photo, if you like. So I'll conclude it there and give some time for questions. Thank you very much for your attention.
Right, thanks, Phil. Just a reminder for the participants on the webinar, if you did want to ask a question, just do so via the Q&A box down the bottom. A few questions have come through. Phil, what's the revenue model for your battery technology and when will revenue start?
Yeah, no, thanks for the question. Certainly the revenue model that we look at from a strategic sense is ultimately similar to the cement and lime industries to license the technology. But there are opportunities at earlier stages. We can look at, if we make a particularly good LMO, there might be opportunities to start to sell that as a cathode material. You've seen in the Chinese data, for example, they're starting to use LMOs to blend into standard chemistries to get the costs down. So we're going to start to look for those opportunities as soon as we can look at the charge discharge cycle performance. If we can prove great charge discharge cycle performance, we'll look to see whether there's opportunities to move the cathode material into existing production lines after if we tick that box successfully within 12 months. Now, it may take some time after that to incorporate the chemistries, but that's certainly probably a little earlier than we'd expected in terms of potential sales revenues.
Just a continuation on that question. Have you had any commercial interest or conversations in the early results of your LMO results to date?
No, the industrial, I guess, participants in the consortia that we have are all obviously discussions continue about the technical development, but at this stage, these results are too early to have those sorts of commercial discussions. We want to see how it performs in terms of a charge discharge stability first. So let us move through that process. But as we do, we'll obviously, if we start to get some interesting early results there, we'll start to progress those discussions as quickly as possible.
Thanks. Next question. Is there any competitive technology being developed that looks similar or better?
We aren't aware of any. We aren't aware of anyone else who starts with a carbonate to make a battery material like this, a manganese carbonate. And while we're aware of other technologies that may have different mixing techniques for different particles to make an ultimate chemistry, for a cathode material, we're not aware of anyone who's using flash calcination the way we are. So it is, we think, a unique processing route to make a fairly unique type of particle that's the basis for the technology.
Next question. What's the significance of the x-axis specific power on the chart on slide 22? Is there potential to extend the Calix LMO to similar levels to the LFP, or is that not significant?
So this is, let me just get my cursor. So this is down to here. So this is where the specific energy runs so low that basically you've taken your battery down to 1/8 of its power output. We didn't bother checking this beyond there because really that part of the curve is a part of the curve that you would rarely operate the battery in. We can extend, but at this stage we haven't. We feel that this is a significant indicator itself of where the battery will be performing.
Right, and just in terms of the patents on the technologies, including the battery work, can you just cover those off? Are they global or by country, etc.?
Yeah, no, we have patents covering the core technology, which is the kiln, the calciner. We have a patent that covers the battery application. That patent has been through its what's called PCT phase and is now in the country by country assessment stage. So that patent, if you like, is moving through the country by country process to get signed off. We've gone to all the major economies with those patents. We haven't gone to every single country in the world, but Europe, the US, Canada, China, and obviously Australia. So we're covering all the major economies with that particular pattern.
And given Europe, China, Japan, and now the US will come under net zero emission commitments by 2050, if all of the cement manufacturers around the world were to shift to Calix technology, can Calix scale quickly enough to meet the very high demand?
Yeah, that's a very interesting question. We've calculated that to put Calix technology across all of those types of cement plants, even if we built a 1 million tonne plant every 3 to 4 days, from now for the next 25 years, we still wouldn't build enough plants to scale to get our technology across all of the cement and lime opportunities. So that's both I guess a challenge, but also I guess an indicator of how big this market is for the CO2 mitigation piece. How we propose to approach the market with respect to business model is move to get to a blueprint for the commercial scale calciner as quickly as we can. So at the end of Lilac 2, hopefully we've got a blueprint that we can then roll out and then look to partners to roll out that blueprint. So there may be a little more development or iteration that takes place, but essentially Calix will not be the one to build these plants. There'll be engineering partners who'll take the blueprints to build. Calix will adopt increasingly towards a licensing royalty type model. So it won't, I guess it'll be a capital and resource light type revenue model as we move through to that licensing phase.
And just a continuation on that question, why is Lilac 1 only running at 80% of nameplate capacity after this period of ramp up?
Yeah, the reason why we're only running at 80%, we've had some still issues at the base of the column, getting the material away. So we've installed air cannons and all sorts of things. It's not that particular constraint has nothing to do with our technology per se. It's just I guess an artifact of the fact that we've built this thing next to the existing plant, and we're putting air cannons in and those sorts of things to keep the product moving. The other thing is we haven't yet run the plant to full capacity. So we're still doing a lot of test work, testing the operational robustness with respect to things like powder build up on the walls, making sure that those sorts of things are not going to impede longer term operation from an erosion or corrosion perspective. But as we move towards the end of the research program, we'll really turn the wick up on the technology. We didn't want to sort of run the risk of melting the tube at this early stage. So we've had an extension on the test program through to mid next year. We've also been impacted a little bit by COVID. We've had both our process engineers come down with it in Belgium, and obviously the interruptions on the plant side itself. So in that extended program, we're going to start to move through to longer test runs and continue to turn the wick up on the tube itself. And so obviously increasing the risk of failure and those sorts of things, but ultimately what we want to do is almost run to that fail so we really understand what it is the technology can do.
Right. And just on your CO2 capture technology, is that membrane based?
No. So inside our little toilet roll, we've got the limestone and cement meal sort of floating down. So they're just particles floating down in the tube. And as they float down, the heat makes them give out their CO2. So half the weight of these lumps of rock are CO2. That comes out of the rock as you heat it. So that CO2 just makes its way back up the tube as a pure stream. So we've tested in Lilac 1 and we've got 95% plus purity out the top of our column. No membranes, nothing. It's just it all happens inside here. Particles fall down, CO2 is released and just goes straight back up the top again. So that CO2 is ready for compression and either utilisation or sequestration.
Great, thanks, Phil. That concludes the Q&A segment. I might pass it back to you for closing remarks.
Excellent. No, thanks, Simon, and thanks very much all for listening. I'm conscious we're 5 minutes away from remembrance and obviously take the opportunity to remember all those in the armed services today. So I'll close it on that and let everyone get off to their ceremonies or whatever it is they want to do there. But thanks again for your attention, and very pleased to have your time to report on our very first year in our battery development program.
Great. Thanks, everyone. Thanks.